In this video, we want to go ahead and take a look at how we test to see if the model works. We have already hypothesized a straight line relationship between x and y, and now we want to go and take a look and see if x is a statistically useful predictor of y. That's the question we want to ask. But before we can answer that question, we got to figure out what does that even mean. So let's go and take a look. Is the independent variable x a useful predictor of y? And so think about some axes here. Let's call this y, and let's talk about this x. And let's say that there is some kind of relationship between x and y. And let's say there's a positive relationship. And so we would draw something like this, right? As x gets large, we would tend to expect to see y get large. And so you'll have this kind of relationship. Well, what if there isn't a relationship? What does that look like? And so let me draw you another picture, and I think I'm going to make sure I'm in a good spot on the page, so I'm not going to overwrite anything else. What does that look like if there's no relationship between x and y? Well, what we'd say there is as x gets big, so as I move this way, if there's no relationship, what we'd be saying is really there's nothing that's going to happen to y. And so as x gets big, we don't seem to see any kind of relationship with y, and so you're just going to have a random scattering. And so here's what will happen. If I try to fit a relationship, if I try to fit a model, a straight line model, it's going to look like this. It's going to be a straight line. Remember that picture we drew where I put in a couple different lines, and one of them was the flat line? I think if you go back, it was y hats equal to 2. Go back a couple pages in your notes. That's what you'd get here. You'd get the sample mean of the y's, and that would be the model that would be fit. And so the way that we're going to do it is by taking a look at our model, we're going to focus on the slope parameter. We're going to focus on the beta that's attached to the x. If x is a useful linear predictor, really another way of asking that question is to ask, is the slope non-zero? And so we're going to do a test of hypothesis that looks like this. We're going to have the null hypothesis is going to say beta 1 is equal to 0. Now in words, what that's saying is x is not a useful linear predictor of y. The null says x doesn't work. The alternative says, oh, yes, it does. And the one I've got listed here, this greater than sign, that's saying that there's a positive linear relationship. You could also do a less than test for a negative linear relationship, or you could do the two-tailed test and test to see if there's any kind of relationship. However, if you think x is a useful linear predictor of y, the natural question I'm going to ask you is, why do you think that? If you think that the size of the house has something to do with the price, why do you think that? And you might be thinking, well, you told us to use it. Why did I tell you to use it? As the size gets big, what do you expect to happen to the price? Well, it should go up too. As the mileage on a vehicle gets higher, you expect the price to go down. You would be testing for a negative linear relationship. So when you're talking about linear regression, here's the argument. I'm going to suggest to you in linear regression that the not equal to test shouldn't be what you're testing. Now, in some other situation, when we talk about multiple regression, the not equal to test may be fair game. But when we're talking about simple linear regression, you should be doing a one-tailed test. It's going to factor into something in a minute. Okay, you should be doing a one-tailed test, and you should know the direction that you're testing. Let's say I make up a new example, and we're trying to predict grades on an exam based on the number of hours studied. Well, what kind of relationship would you expect? The more somebody studies, the higher the grade should be. And so that's the kind of thought process that needs to take place. I want you to go and think about the relationship between the variables and then choose the one-sided test, the one-tailed test, the one-directional. Is it a positive linear relationship like I have up here? Or is it going to be a negative linear relationship like the automobiles? Now, the way we do it, this is just a test hypothesis. We've been doing these all semester, right? This is just a test, a hypothesis. We need a test statistic. Hey, there's a fun formula, right? We don't do formulas. We're going to let the computer come up with that number for us. But I do need you to interpret those results. And so when we go to the printout, we're going to use the p-value approach. Now, what's the p-value approach? Well, you know how to do it. If the p is low, we're going to reject that null hypothesis. Another way of saying it, if alpha is greater than the p-value. We reject the null hypothesis. We're going to conclude that X is a useful, positive or negative, depending on what we've tested, linear predictor of Y. The other possibility, fail to reject. If our P is high, we fail to reject. There's insufficient evidence to indicate X is a useful predictor of Y. And of course, anytime you're making an interpretation or a conclusion in a test hypothesis, I want you to do that in the words of the problem. So tell me about sizes and rents, or sizes and prices, or mileages and prices. I want you to talk about the variables involved. All right, so here's the example. Here's the one we've been working with as we've gone through this. We want to predict the sales revenue using advertising expenditure, and we've seen the printout. I'll show it to you in just a second, but which would be the test that you would conduct here? As you spend more in advertising, what do we expect to happen to the sales? Well, if you're in any kind of marketing or advertising, what are you going to say? As advertising expenditure goes up, we'd expect sales revenue to go up as well. So we're going to do a greater than test, and here's that printout. Okay, now in step 1, we hypothesized the model. In step 2, we estimated the betas. We get that right here. In step 3, we stated some assumptions, and we looked at our standard deviation down here. Here, what we're going to do is a test hypothesis. So the test statistic, it's a t-test. Whenever we're testing just a single term, it's called a t-test. It's right there. And then you have this p-value here. Now be careful about this because, and I can't show it to you in this video, we're using this program Office Mix to do this video. I can't really toggle back and forth between the PowerPoint notes and the statistics software, but in another video you'll see how we generate this printout, and this will be the first time, no, not the first time, but it's one of the few times where we don't get to choose the direction. A lot of the tests that we've conducted this semester, we've had a greater than, a less than, a not equal to option. Those are the 3 options that are available for the alternative. And again, I don't think the not equal to is the one to do. But this particular test doesn't ask us which test we want to do because it assumes we're doing a two-tailed test. And that's a problem. Because as I mentioned a little while ago, we're not doing two-tailed tests. We're doing one-tailed tests. And so this is that moment of truth. We've been talking about p-values and how to manipulate them or how to change them to be the values that we need them to be. We need to do that here. This is a two-tailed p-value, and I'm telling you, you're not going to do a two-tailed test. You're going to do a one-tailed test. So we need to change that p-value. The test statistic is 3.66. The p-value, we're going to take the numbers on the printout and divide them in half. If the two-tailed p-value is 0.0354, the one-tailed p-value is half of that, and that's the one that's appropriate. And so the p-value that we're going to use in our test hypothesis is 0.0177. And now I want you to write a conclusion. You choose the alpha. What would you say? How about something like, oops, thought I hit the right button. How about something like this? At alpha equal 0.02, we reject H naught. And I know you're looking and saying, wait a second, that's not your p-value, right? You got to divide that in half. That 0.0177, compare your alpha and the 0.0177. P is low. We can reject. There is sufficient evidence to indicate that advertising expenditure is a useful, positive, linear predictor of sales revenue. You could say advertising is a statistically significant, positive, linear predictor of sales revenue. A lot of different words you can use here. You got to get across the point that there's a positive relationship between these two variables and say it in the words of the problem. That's the test hypothesis. That's what we want to do here in, what am I in, step 4. And so technically that's the test we want to conduct. Now I'm going to add 2 more pieces here. There are 2 measures that are going to talk to us or speak to us about how useful our model is. And so this is the test to see if the model is significant, or test to see if the model works. I think that's how I wrote it on the 5 steps. But there are 2 other measures that will help us understand the usefulness of the model. The first one, and it's one I mentioned already, it's called the coefficient of correlation. And the coefficient of correlation, the symbol that we use is R, and it measures the linear relationship between X and Y. Ranges in value between -1 and +1. If you have let me draw a couple of little pictures over here for you. This is Y, this is X. If you had points that look something like this would be a correlation of maybe like a positive 0.7. If I had something that looked like this, let's see if I can do this one now. Let's say it looks something like this. this might be a negative 0.3. If there's no correlation between two values, so if there's no linear relationship, as x gets big, y doesn't tend to do anything, this would be a correlation of 0. That's how they work. 0 indicates no relationship. The positive and negative 1 is, as you get closer to them, the strength of the relationship becomes greater. Negative is a negative correlation. Positive is a positive correlation, obviously. Here's the picture that causes us trouble with the coefficient of correlation. Because the R, or the correlation coefficient, if we were to fit a straight line to this model, this is what it would look like. We would fail to reject. There's insufficient evidence to indicate there is a linear relationship between x and y. And we would say x is not a useful linear predictor of y. And that's a true statement. Problem, of course, is it's an extremely good curvilinear predictor of y. X is extremely useful at predicting y. It's just not a linear relationship. And so I had mentioned at the beginning of all this simple linear regression that we could take about 20 minutes to talk about the coefficient of correlation. There's actually a test hypothesis. There's a confidence interval. We could look at just the correlation to talk about linear relationships, but that limits us. And we don't want to limit our discussion to just linear relationships between two variables. And so this is how the coefficient of correlation works. A couple of comments here. 0 is no linear relationship. Plus or minus 1 is a positive linear relationship. But we don't want to limit ourselves that way. And so we don't talk too much about the coefficient of correlation. I know we're talking about linear relationships here, right? Simple linear regression. But remember what I had said. We're using the simple linear regression as a stepping stone to the multiple regression. We want to get more complicated in this. We want to allow for more complicated relationships. Sometimes straight lines are all you need. Most times not. Most times you need other variables, other relationships between the variables. And so we'll look at that in the multiple regression topic, but the coefficient of correlation comes up here. There will be one place where the coefficient of correlation can be useful. When we get to the multiple regression topics, sometimes we want to look for simple linear relationships between some variables, and we can do the coefficient of correlation. I'll mention it when we get there. It's called residual analysis. But for now, we'll just mention it as a numerical descriptive measure, but really it's not the one that we're going to spend a lot of time on. So I bring that up. However, the one that we are going to spend some time on, the one that we will use, is called the coefficient of determination. Great name, right? Coefficient of determination. You see a y bar there. There we go. There's a formula, and all these numbers show up on the printout somewhere, but really this is a number that you'll get right off of the printout. I'll show it to you in a second, and we'll talk about it. But it's a useful number. SSYY. This is talking about variation in the y's, unexplained error of the y-bar model. So earlier I had that picture where we had the points for our little example, and I draw two curves, and if I remember correctly, this one was the blue line, or I drew two lines. That was the blue line, and then there was a red line that went like this. That was supposed to be a red line. Let's try that again. Maybe it'll be purple now. There was a red line that went like this, and I tried to talk you through and say, hey, the red line's better than the blue line. Of course, it wasn't that hard to convince you of that. These two pieces, the SSYY, the SSE, they're different sums of squared error. It's the part of the y's that we can't explain. This one uses the y bar line. This one uses actually the y hat line. And so the idea is, how much variation is left in the y's? How much variation in the y's can we still not explain? One of them says, well, don't use the x's, that's the SSYY, and that would be kind of the worst case scenario. If you didn't use the x's, that's how much error there would be. And it's saying, well, if you do use the x's, this is how much error there is, and really we're comparing those two. I'll give you an idea here in the next picture. Let's go over here. R-squared compares the model that uses the x's to the model that does not. And so really it's trying to answer this question. How much better off are we using the regression model than if we just used y-bar? How much better off are we using the x's than not using the x's? It's comparing. R-squared is always going to compare two models. It's taking a look and saying, well, look at how much you missed by here. That's the errors. That would be the SSE. That's that 1.1 that we saw in the printout earlier, versus how much did we miss by here. And if you remember earlier, that value was 6. That one got it perfect down here. The SSE of the Y bar line was 6. And so we really do a little bit of math. We compare the two. So we know the 6 is the SSYY. And then we have 1.1. That's the SSE of this line here. And you divide by, you say, all right, well, so I've explained 4.9 of that 6. And this is the number that you actually see on the printout. Now, if this picture helps you understand what R-squared is trying to do, that's fine. If it doesn't, that's fine too. It's trying to show us, it's trying to quantify for us, maybe say it that way, the value that's added by the x's. We're explaining almost 82% of the variation in the y's. That's pretty good. That using x in the model has taken the variation that was there, the 6 that was there when we didn't use the x's, and it's reduced it considerably in this case. And so the way that you're going to see me interpret R squares is going to look like this. Okay, first, there it is on the printout right there. And this is how we're going to interpret it. Almost 82, 81.67, almost 82% of the variation in the sample y values about their mean. That's that y bar variation. Can be explained by using advertising expenditure in the linear model. By using the x, by using the advertising expenditure, we have reduced the variation in the y's that is unexplained. That's a big deal. That's a big chunk right there. And so the coefficient of determination gives us a feel for the improvement that we get by using the x's in the model. And I'm saying x is. There's only one x now. We're talking about simple linear regression. But the beauty of the coefficient of determination, the reason that we're going to take a little bit more time with this one than the correlation coefficient, is that this idea moves forward. It works here with the simple linear regression. It's also going to work with multiple regression as well. And so the coefficient of determination is definitely an interpretation that you want to take a look at seriously, and you're going to need to understand. Okay, now a couple notes. You'll notice that first there's the R squared, and so let me just kind of mark this up a little bit. We looked at these guys here. That was the model. We looked at the standard deviation when we did our assumptions in step 3. We just did a test of hypothesis, and we looked at this guy. And now I'm going to kind of highlight both these things because look what I have. I have an R squared, and I have an adjusted R squared. I'm going to talk about the R squared, but you'll see why I'm talking about, or I note the adjusted R squared with some of the notes I'm giving here. First, R squared talks about the percentage of the variation we can explain. Well, shoot, we'd like to explain all of it. Can't do it, but we'd like to. And so ideally, we'd like to explain 100%, which means bigger R squares are better than smaller R squares. That's a good thing. It's a natural thing to notice. It's also a dangerous thing. Here's why. If all you're paying attention to on R squared is R squared, then your tendency is to want to get R squared as big as you can. And a problem with that is R squared can be artificially increased by adding x's into the regression model. And I say useful or not. What does that mean? It means if I'm trying to predict the price of a house, the size of the house is an important variable. It's going to make R squared bigger because it's going to explain some of the variation in the prices. Maybe the size of the land or the lot that the house is built on. Maybe that's an important variable as well. That's going to make R squared go up. The location variable that we work with in multiple regression, maybe that's significant too. R squared is going to go up. And so as you add these useful variables, R squared is going to go up. But here's the issue. What if you add some variables that aren't useful? What if you start making up weird stuff like whether the front door is painted red or not? Use a variable. Is the front door painted red? Yes or no? Well, you're probably thinking that's a dumb variable. It is. I agree with you. That shouldn't be useful, but here's what I know. By simply adding that variable in, R squared is going to go up. Here's one of my favorites. Now keep in mind, my last name is Dummeldinger. I think a variable should be, or I hope a variable is, the number of letters in the owner's last name. That should affect the sales price. Because as a Dummeldinger, I'm going to say the more letters in your last name, the higher the sale price should be. Now, hopefully you're shaking your head thinking, no, that doesn't work, especially if you have a really short name. You're probably thinking, oh, I hope that's not the case. But that's foolish. That's a ridiculous variable. But here's what I know. Mathematically, R squared is going to go up. And so the coefficient of determination is a useful little number to look at, descriptive measure, but it can be manipulated as well. If I'm going to choose which model, and again, this is more of a multiple regression idea. Remember we talked about having to select which model is the best one. If I'm going to use R squared as the technique to choose the best model, I'm in trouble because R squared is always going up as I put variables in. So if I'm using R squared as my decision maker, it's going to tell me use more variables. Keep putting variables in it. You're going to say, oh, I'm going to choose the biggest model, and that will always be your decision, which is a terrible decision. And so there's two choices here. One is we can use adjusted R squared to eliminate that problem. It's got the similar interpretation as R squared, but it doesn't contain the drawback. The way that it's calculated will take into account whether the variable is useful or not. And so if you're stuck on the idea, I'm going to use this R squared idea as a way to figure out what model is the best one to use, adjusted R squared be the one you should look at because it'll lead you in a better direction. The other way of working this, and this is the way that we're going to do it, is I don't care so much about adjusted R squared because I'm not going to use R squared to choose my models. We're going to have a model building technique. And if we follow that technique, it involves working with some test hypothesis. We're going to be interpreting p-values. Yeah, p-values. That's it. When p is low, we're going to reject the null hypothesis. How about that? Now, there's a whole lot of information to learn to figure out how that's going to apply, but that's the model building that we're going to do. That's the technique that we're going to use. And so R squared's out of the picture. We don't look at R squared until we say, here's our best model. And if that's your approach, which I want it to be, then you can go ahead and interpret the R squared you see on the printout because you're not using it inappropriately. You're not using it for something that's not intended. You're using it to say, all right, here's the model we're looking at. Let's talk about the percentage of the variation in the Y values that we can explain. And so the coefficient of determination is a really good number. It quantifies for us. We can explain almost 82% of the variation in the sample sales revenues using advertising expenditure. Dang, that's good. One little variable explaining 82% of the variation. Good job. And so that's our coefficient of determination. So in step 4, and that's kind of the end of step 4 here too, I'm going to summarize here. In step 4, we're doing a test of hypothesis to determine if there's a slope, if the x is actually a useful linear predictor of y. Again, choose your slope wisely. Is it a positive slope or a negative slope? You should know. In simple linear regression, you should know the shape that you're looking for, the direction of the slope. Do a one-tailed test, but by doing a one-tailed test, be careful with the p-value because that's a two-tailed p-value. There's no way around it. The p-value on the printout will always be two-tailed. The test you want to conduct here is always going to be a one-tailed, so you have some work to do. I'm going to split it in half. And then once we get our model, the R squared value, the coefficient of determination will be on there. I want you to do an interpretation of that. In simple linear regression, just a math trick I'll show you here. In simple linear regression, the correlation coefficient and the coefficient of determination are related. R squared is the correlation coefficient squared. That will change as we move forward. That's not going to be the case in multiple regression, so I don't mention that too much. But this coefficient of determination will move forward. Correlation lives and dies with lines. Coefficient of determination moves on with us. So it's an important interpretation for you to understand. All right, so that is the end of step 4. So the only thing that's left. All right, in this video, we have one more step remaining. We're going to do the final piece, and that's where we use the model for estimation and prediction. So the story to get to this step would be we've hypothesized a straight line relationship, we've done our beta estimates, we've made our interpretations, we've stated our assumptions, we've estimated a standard deviation and interpreted that, we've done a test, and we've said at this point that the model is statistically useful. The p-value is small, we've gone and we've interpreted the R squared value, and now we want to use it for estimation and prediction. And we've talked about these two parameters, I'll call them, before. Y is a single value. So the single price, or let's say it this way, the price of a single car with 40,000 miles, E of Y would be the average price of all cars that have 40,000 miles. The rent of a single apartment with 800 square feet, the average rent of all apartments with 800 square feet. So that's the difference between Y and E of Y. And the way that we're going to go about it is we're going to use a confidence interval. And so those two parameters again, y and e of y. You should know that the predicted value in statistics is the y. It results in a wider, it's harder to predict a single value of y than it is a mean. So the prediction intervals will be the wider, but you're going to find that in the predicted column of the statistics printout. E of y is going to be the average of all. Okay, the mean value for all y's that have a particular setting of the x's. And that's referred to as the fitted value. Terrible name, it should be mean. But it's called fitted on the printout, and it's actually on the right side. And it's the narrower of the two intervals when you compare y to e of y. But there's another piece to this puzzle in terms of the formulas. The intervals are always narrowest when you use a value of x bar as the prediction value. So if your homes range in size from, say, 2,000 to 4,000 square feet, and your average is 3,000, pretty big homes, I guess. But if your average was 3,000, using a value of 3,000 square foot as a fitted value, or as a predicted value of x, would give you the narrowest interval. If you go to 2,000 or 4,000, the intervals get wider the further you get from that x bar value. Not a huge deal, and typically you don't choose the value of x bar or predict a value because it's the value of x bar, but it is an interesting little piece. All right, so here's what we get. This is kind of a confusing little picture here. Here's y, and you can't really see it. It's a tougher axis to see, but think of this as the x-axis down here. And this value right here is the average value of x, so the average size of your house, the average mileage of your used cars. The confidence intervals for e of y are this red dashed line here, and the intervals are narrow. So you're going to see the endpoints. You're going to see this value, and where am I, about maybe like here. You're going to see those two values show up on the printout. As you move away from x bar in either direction, the intervals get wider. The yellow dash, what appears to be yellow on my screen at least, dotted lines represents the prediction intervals. So this would be y, and these are the e of y's. And so that's just a little diagram showing you how the interval widths are related to one another. Main thing I want you to be able to do is to be able to get the printouts and then make an interpretation. And so the printout I have here is saying, what if we spent $250 on advertising? And there's a couple different ways of generating these printouts. There's one called the case number method. That's not the right name. And then there's one where you just put in the data values themselves when you get into statistics. Again, I'll go through another video and show you how to generate these printouts. But each of the printouts is going to have a value of x that you're working with. In this case, it's 250. I put that value in. I use 2.5 because $250 in hundreds of dollars would be 2.5. There's the confidence level, which you can change. And then these numbers here is a prediction interval. You see the predicted values. And over here, this would be the confidence interval. So this is e of y, fitted. These are the e of y's, and the y's are on this side. And so the numbers show up on the printouts. What I want you to be able to do is interpret these values. So I'm going to talk about them while we're looking at this printout, and then you can see them on the next page of notes. That's where we think y is. However, we want to be real careful how we say this. That's where we think y is when the value of x is 2.5. And we have 95% confidence. So we're going to go back. This is just a confidence interval. And I don't care whether I call it a prediction interval or a confidence interval. The wording is sort of irrelevant. These are both confidence intervals. And the way that we state confidence interval interpretations, we are 95% confident that something falls between these numbers. Something falls between these numbers. And so let me go to the next page. We are 95% confident that this is for E of Y now, right? The mean sales revenue for all months when X is equal to 2.5, when advertising expenditure is equal to 250. What's going to happen if I change advertising expenditure? My endpoints are going to fall in thousands of dollars, right? In thousands of dollars. That's why on the printout we see the number 0.7359 and we see 2.5641. in thousands of dollars. We are 95% confident the mean sales revenue for all months when advertising expenditures $250 will fall between those endpoints. The other numbers were negative 0.4829 and 3.7829. We are 95% confident that the sales revenue for a single month when advertising expenditures equal to $250 falls between, what did I say those numbers were, 0.4829, that's a 483, and 3.7829, $3,783. Now, in this particular example, one of the things that's a little challenging, I think, I tried to make the numbers easy. That's why we went with 1 and 2 and 4 for the sales revenues and the advertising expenditures. It's a little trickier than your typical printout because we're having to adapt. We're trying to take that point 7359 and I'm making that $736. And if you want to be really picky, $735.90. So I'm having to take the values of Y that we see on the printout and make them thousands of dollars. The values of X that we see on the printout, we're making those hundreds of dollars. So that's a little bit of a challenge here. Most of you guys don't have to worry about this because you entered your miles as miles. You entered the sales prices as dollars. So you can interpret them as a look on the printout. But this is the fifth step. Fifth step's pretty easy. It's just doing a couple confidence intervals. Picking the value of X that you want to work with, and then stating the confidence interval for E of Y, the prediction interval for Y, getting those on the printout, and giving me a practical interpretation. Should be, I hope it is, pretty straightforward. We're getting long in the semester here. We've done a lot of work now. If you're still struggling with confidence interval interpretations and p-value interpretations, you're way behind at this point. You got to go back and review and get up to speed quickly because you're very quickly running out of time. So hopefully that makes sense to you. I want to go ahead and take a look at an example using this data set, the Diamond data set. I'm going to post the Diamond data set in Canvas so that you can go ahead and practice with it. And I'll come back in another video and go through and talk our way through all the different pieces of a simple linear regression analysis. So until then, so long.